Activities conductometric estimation of acid mixture using standard sodium hydroxide. So the analyte sample given today is an acid mixture having strong acid and a weak acid. Strong acid means which ionizes completely, weak acid means which ionizes partially. Example for strong acid, hydrochloric acid, sulfuric acid, nitric acid. For weak acid, it is your acetic acid or formic acid. One such strong acid and weak acid are mixed and given in a beaker. Okay, and you need to calculate the amount of that strong acid and weak acid mixed in this given volume. So to calculate this, we require Ohm's law. According to Ohm's law, V is equal to IR, where I is the current and R is the resistance. And we are here calculating or using the instrument called conductometer, which shows the conductance value. What is conductance? It is the reciprocal of resistance having the unit ohm inverse, centimeter inverse. So particularly we are measuring here the conductance called specific conductance having the conductivity cell which contains two electrodes which are made up of platinum electrodes, okay, and the platinum electrodes are having the cross sectional area 1 square centimeter, and the distance between the two platinum foil here is 1 centimeter. So whatever the specific conductance you measure using this type of conductivity cell is called as specific conductance. So we are measuring specific conductance here using the conductometer. So the experimental setup is made or done like this. So dip the conductivity cell inside the acid mixture given in the beaker, switch on the magnetic stirrer, fill the microburette with the given standard sodium hydroxide solution. It is a base, reacts with acid mixture, neutralizes it into salt and water. Let's see the variation in the conductance and note it down in the tabular column. The tabular column is the first column, volume of sodium hydroxide, which is added at an increment of 0.5 ml, and the second column is conductance, which is expressed in terms of ohm inverse, centimeter inverse. So initially, without adding any sodium hydroxide, note down the conductance which is purely for this acid mixture. So 1.39. Okay, so if there is a fluctuation between two readings, you fix it to the one reading. So I am fixing to 1.39, the lower one. So now accurately add 0.5 ml of sodium hydroxide and observe the change in the conductance. So 0.5 ml is now going into the acid mixture. The magnetic stirrer is stirring the solution and you can see the change in the conductance. So after adding 0.5 ml, there is a increase in the conductance value because the hydrochloric acid, which is an example for strong acid, okay, so first reacts with sodium hydroxide, neutralizes into, okay, salt and water. When hydrochloric acid neutralizes, okay, so H plus ions are replaced by the slow moving Na plus ions. So conductance value here decreases 0.83. Now the next 0.5 ml is going into the beaker. You can see the decrease in the conductance value as the hydrogen ions are reacting here, 0.64. The next 0.5 ml. As long as there is hydrochloric acid, hydrogen ion, okay, there is a decrease in the conductance value. When all the hydrochloric acid is completely reacted, let's see what happens. The next 0.5 ml is going into the beaker. And you can see 0.61 in the previous reading. Now it's increased to 0.66. That means you got the first end point here, which is considered as V1. Okay. So now it's the turn of our weak acid. For example, acetic acid if we have given, it reacts now with the NaOH that is added from the burette. Since acetic acid is a weak acid. Its conductance is little bit lower value, but as the acetic acid reacts with NaOH, it forms a strong electrolyte of sodium, that is sodium acetate. As a result, we observe the gradual increase in the conductance value. So, in the conductometric experiment, there is a decrease in the reading first. After the first endpoint, we get the slow increase, and let's see what happens next. Okay, there is a gradual increase in the reading that we are noting down here, and when all the acetic acid is also completely reacted with this base, you get the next endpoint. And what happens at that end point? All the acetic acid, after completely reacting, we left with only sodium hydroxide, which is a strong base whose conductance is again very high. So you got, see, 0.87 to 1.24. You got the second, okay, so end point or the jump in the reading. So after which you need to take down the few more readings to plot a graph. There is a gradual increase again, okay. So you note down that readings. It is due to sodium hydroxide, the strong base containing OH or hydroxyl ions. So initial decrease is due to hydrogen ions neutralization, and the second gradual increase is due to the acetic acid, and finally it is due to our sodium hydroxide. Note down all the readings, and now you need to plot a graph. Okay, so by taking the conductance value, go on taking the reading, and you get the readings like this. See, there is a gradual increase. Okay, so increase in the value, then again increases. Okay, and then there is a slight or sharp increase. So take all the 8 up to 8 ml, you take the readings. Now when you plot a graph here, volume of sodium hydroxide against conductance, you can clearly see the points here. There is a decrease, gradual increase and a sharp increase. When the intersect met the x-axis, you got the two volumes which are called as V1 and V2. Note down the V1 and V2 values and calculate the amount of acetic acid as well as hydrochloric acid, okay, that is given in the beaker using the formula. So the first formula is, let's see first, estimate the amount of hydrochloric acid using the formula N1V1 is equal to N2V2, normality of hydrochloric acid. So sodium hydroxide is a standard solution whose normality is given. Then what is V1 obtained from the graph? What is the original volume taken in the beaker? 50 ml. So you got the normality. Then you express it in terms of weight. Weight in terms of grams. It is obtained by multiplying by the equivalent weight. So this is for hydrochloric acid, and you calculate for CH3COOH or acetic acid separately. Here the formula is N of NaOH into V of V2 minus V1. V2 minus V1 gives the amount of, okay, or volume of sodium hydroxide required to neutralize your acetic acid. So you get the normality first, multiply it by equivalent weight, you get the weight of acetic acid. In this way, you can calculate both the weight of hydrochloric acid and acetic acid using the conductometer.